Hello and welcome back. Lecture 3-1S is the odometry-based motion model example. Use the odometry motion model to find the probability of controlling a mobile robot from an initial pose of 0, 0, 0 to a final pose of 1.8, 0.75 pi over 4. Given a control input from the wheel encoder measurements that measured an initial pose of 0, 0, 0 to a final pose of 1.85, 0.77, 0.81. Assume all motion error parameters are 0.05 and the motion error is modeled with a normal distribution. The movement of the robot is dictated by the wheel encoder measurements as shown in the figure here and converted to a rotation, translation, and then another rotation to get the final orientation. So the control input UT is x bar prime, and as previously stated, alpha is equal to 0.05. The noise model for odometry-based modeling for motion modeling is given by the following formula. We are going to have delta hat of rotation 1, delta hat of the translation, and delta hat of rotation 2, where that represents the desired rotation to get from the initial to the final position plus the addition of noise. And we will use alpha to represent our noise variable that's added onto that. So here are the three equations that we're going to use for the noise model for odometry-based motion modeling. We're going to model the probability of having that noise based upon a normal distribution probabilistic motion model, which is given by the equation 1 over the square root of 2 pi b squared e to the negative 1/2 a squared over b squared, where a is the query point, which we will assume is a zero mean, and b is the standard deviation, or b squared is the variance. So we will pass in the probabilities for each of these terms, the two rotations and the translation, in order to get the probability. So here is the algorithm that we're going to use in order to find the posterior probability for the odometry-based model. So the input is odometry, which can be in terms of x bar and x bar prime, which we also call our control input. So we can get those by finding delta trans, delta rotation 1, and delta rotation 2 by using the square root, arctangent, and then adjusting for the final orientation of the robot. Then we look for our modeling errors for these values, which are our values of interest for x and x prime, by finding delta hat trans, delta hat rotation 1, and delta hat rotation 2. And then finally, we are going to use our normal distribution probabilistic motion model in order to find the probability for these values. And that's going to be P1, P2, and P3. And finally, our result will be the product of those three. So in our first section, we input all of the values from the problem statement, including our initial value, our final value, as well as the values from the x, y, and theta for the odometry measurements. Then the next section is our control input, and this is the section based upon our odometry parameters. Then our next section is our translation and rotation values based upon initial and assumed final values for the robot. So if we run that, we get that delta rotation 1 is 0.3948, delta translation hat is 1.95, and delta rotation 2 hat is 0.3906, as compared to what we got from the odometry, which is delta rotation 1 of 0.3944, delta translation of 2, and delta rotation 2 of 0.4156. Finally, for our modeling error section, we will have that alpha equals 0.05, like in the problem statement, and we will then find our mean values as our delta rotation 1 minus delta rotation 1 hat, delta translation and delta translation hat, and the difference between delta rotation 2 and delta rotation 2 hat. And then we multiply that by alpha for our modeling errors for our rotations and translations. And then we pass that in as the mean and the standard deviation into our normal probability distribution as given by this function here below. And when we run this, we will see that we get that P1 is 0.8967, P2 is 0.8738, P3 is 0.8957, and the overall probability that the robot reaches that final location is 0.7018. Thank you for coming. Thank you for listening. I hope you've enjoyed it and have a robotastic day.